this lecture, I'll be discussing some of the important features of power system protection. Power system protection. So we can say that the power system protection or the protective devices that we have installed to protect the power system are well performing if the power system protective devices are exhibiting these features that I am showing here. First one is reliability. Second one is selectivity. Third one is sensitivity. And fourth one is economical. So the devices should be of low cost. So these are the desired features that the power system protection should exhibit. I will explain each one of them. Let us start with the reliability. Okay. So reliability is a very general term. When do we say someone is reliable? If I give a task to someone to perform, if he is performing the task perfectly, then I can say that the person is reliable. Okay. So I can give him another task and I can relax, sit, lean back and relax because I trust him now. He's reliable and he's performing the task perfectly. Same thing applies to power system protection also, protective devices also. If the protective devices are performing their intended duty, then we can say that the protective devices or the protection system is reliable. So first I will write the generic definition of reliability. So reliability is the measure of degree of certainty that a piece of equipment performs as intended. So we have some equipment with us, a piece of equipment, and if it is able to perform the given duty, or given it is able to perform the intended duty, then we can say that the equipment is reliable. Similarly, our protective devices here, here this piece of equipment in our context may be a relay and circuit breaker, right? In the context of power system protection, if relay and circuit breaker are able to perform the assigned duty, then we can say that these relay and circuit breaker are reliable. Okay. So unreliability, when do we say that they are unreliable? Here unreliability is because of two reasons. In power system protection, unreliability may occur because of two reasons. The first one is that protective devices fail to operate when needed. Okay, protective devices fail to operate when needed. So that is the first reason for unreliability. So if the relay and circuit breaker do not operate for a fault which they are responsible to isolate, in that case we can say that the protective devices are unreliable. Okay, there is one more reason for unreliability. It is that protective devices operate when not needed. Okay, so these two are the main reasons we can say when this relay and circuit breaker become unreliable. Okay, it might be because of reason 1 or because of reason 2. Unreliability might be because any one of these reasons. I will give you an example for you to easily understand this unreliability. Let me take a small portion of a large system. So there are two bus bars A and B, and we have a line joining these two bus bars, and there is other power system here. I'm not showing the entire system. We are concerned about this small zone A and B and the line joining between A and B. So to protect this line joining between A and B, we have installed circuit breakers here. Okay, let us suppose this is breaker 1 and this breaker 2, and there will be obviously a relay corresponding to this breaker and relay corresponding to this breaker 2. Similarly, for each line, there are breakers. This is B3, this is B4. Of course, there will be relay R3 here and R4 here. So because relays has to initiate the operation of breaker, relay will sense the fault and it will initiate the operation of breaker. Let us suppose there is one more bus bar here, and we have a breaker and a relay combination here also, B5 and R5. Obviously, there are breakers here also. Anyway, so there are a set of breakers and relays protecting the transmission line. So now coming to our zone of interest between A and B. If there is a fault in between A and B, so fault in A and B zone, okay, in between A and B, then relays R1 and its corresponding breaker B1 as well as R2 and its corresponding breaker 2 should operate. See, there is let us suppose there is a fault here. So this fault, let us take it as a mesh system. So fault may be fed from this direction, or fault may also be fed from this direction. Okay, sometimes one direction or both the directions. If there are multiple generators and it is a ring kind of system, then fault might be fed from both the ends. So that is the reason we have kept two breakers here. Here, to isolate this fault, this whole relay R1 B1 as well as relay R2 B2 should operate. For this fault, if R2 and B2 fail to operate, then R2 and B2 are not performing their intended duty. So we have designed the system in such a way that if a fault occurs between A and B bus bars, R1 and R2 and their corresponding breakers should operate. If they are not operating for any reason, that reason might be secondary. But if they are not able to operate, then we say that this system is unreliable. Here, unreliability is because of the first reason. Productive devices are failing to operate when needed. Here there is a fault in between zone A and B, and it is needed for the relays to operate, and they are failing to operate. This is one of the reasons for unreliability. Okay, if we see this fault current coming from in this direction is being experienced by these relays also. Here R3, R5 are also experiencing this fault current, but we have designed the system in such a way that R1 and R2 should operate first, and they should initiate the breakers B1 and B2. When B1 and B2 will open, this section A and B gets isolated. See, if B1 opens, fault current cannot be fed from this direction. If B2 opens, fault current cannot be fed from this direction. So the design is such a way that fault gets completely isolated. If R2 B2 fails, or before operation of R2 B2, if R5 has operated, okay, if R5 has operated and it has triggered the operation of B5, breaker 5, and breaker 5 has opened. So this happened before R2 has acted. Why this has acted? Because it is also experiencing the fault current, but it is not intended to operate. We have designed the system in such a way that R1 and R2 alone will operate first. How we have done this kind of coordination arrangement, that is secondary, that we will discuss when we go ahead within the course. Okay, so before R2 and B2, R5 has operated for a fault that is not present in its zone. Okay, here for fault between A and B, what I'm trying to tell is R5 and B5 has operated. Okay, so they are not intended to operate for a fault between A and B, but they have operated. Okay, R5, B5 operated before R2 B2. If R2 B2 and R1 B1 operates within the given time, the faults get isolated like this, and fault will not be fed from in this direction. Okay, but before this could happen, this relay, because of some mal operation, it has operated and it has initiated the operation of circuit breaker, and there is an opening here. Now this fault is cleared by this relay, because fault is no longer fed in this direction because of this relay. So here R5 and B5 are not intended to operate, but they are still operating. So this is one of the reason for unreliability. Here unreliability is because of the second reason. Productive device operate when not needed. Here R5 and B5 should not operate before R2 and B2, but they have operated before R2 and B2, and they have isolated the fault. Well, you can say that they have isolated the fault before R2 and B2, then the fault got isolated and the system is protected. Well, the system got protected, but what about the load connected to R5 and B5? Okay, there is a load connected here, let us suppose. So if R5 and B5 are opening, so what happens to the load connected to this feeder, or what happens to load connected to this feeder? Okay, so these are the two reasons for system being unreliable, and both of them are not desired. Coming to the second important feature, that is selectivity. So this is slightly related to reliability. Okay, selectivity means the productive devices should exclusively isolate the faulty section. Okay, so the whatever productive devices, circuit breakers and relay that we are deploying in the power system, they should exclusively isolate only the faulty section. The healthy section should remain intact. I will give you an example for better understanding. Let us take a simple distribution feeder, radial distribution feeder. Okay, so current is flowing in this direction only, and it's a radial feeder, so obviously current will flow in single direction. So we have loads connected at every bus bar. So let us name the bus bars A, B and C. So we have installed some relays here. Okay, obviously there I'm just showing a cross. It indicates that relay and circuit breaker are present here. I'm denoting them as R1, R2 and R3. Of course, there will be a circuit breaker also along with R1, because relays are not standalone devices. They have to be used along with circuit breakers. But I am not showing them here for simplicity. So if I take R2 as a reference relay, the relays that are right side of R2 are called downstream relays. And those relays on this side are called, left side of R2 are called upstream relays. Upstream relays and downstream relays. So these are the downstream relays. These are the upstream relays. Okay, if R2 is taken as reference, same applies with to other relays as well. Okay, I'm just erasing this. So for R2, R3 is the downstream relay, and R1 is the upstream relay. Okay, if there is a fault here between B and C, R2 should operate. Okay, fault between B and C. So which relay should operate? R2 should operate. So how the fault is being fed? Let me show you how the fault is being fed. So since it is a radial system, current flows only in one direction. So fault is being fed in this direction. So current is not coming from in this direction. There is only load. There is no generator on this side. R2 should isolate, should detect this fault, and it initiate the operation of its corresponding circuit breaker, and the circuit breaker should open. So there will be an opening here, and this fault should get isolated. Okay. But what happens if R1 has operated instead of R2? Okay. Because R1 is also, after all, seeing the current, fault current. So there is a chance for R1 also to operate, but we have not designed the system in such a way for the R1 to operate. We have made R2 to exclusively operate between B and C. How that is made, that is again a different aspect, as I told you again. Okay. So between B and C, if there is a fault, R2 has to operate. But by chance, if R1 operates, what happens? If R1 operates, there will be an isolation here. Circuit breaker here will open, and the current will not go into the feeder. The current will not go into the feeder. If R1 operates, current comes up to here, and it can feed the load. I will show you another color. So current comes up to here and can feed, and the load here can be fed. Okay. If R2 alone has operated, because there is an opening here, only this portion is isolated, and whatever loads that are connected beyond B and C, okay, will get affected because of R2 opening. If R1 opens, this whole network gets isolated, right? If the load is connected here, if the load is connected here, that will also not receive supply. Okay, if R1 opens. Okay, so in this case, if R1 is opening instead of R2, then the system is not selective. Okay, so the productive system should exclusively isolate the faulty section. So the faulty section is B and C. So relay R2 has to operate, and this section has to be isolated. If the productive system is able to do such that only B and C faulty section is isolated, then it is said to be a selective system. Okay, that is one aspect of selectivity. The second aspect of selectivity is that productive devices are able to discriminate between faults and transient conditions. Okay, transient conditions like magnetic, inrush current, or some surges on the power system. Okay, so these transient conditions that last for a momentary seconds, power system relays and circuit breakers, the productive relays and circuit breakers should tolerate this transient conditions. Even though the magnitude of current is high, they should be able to discriminate between an actual fault and a transient situation. If the productive devices were able to discriminate between transient conditions and faults, and if they are able to restrain, it means they remain unoperative. They do not operate under transient conditions, and they operate only under fault conditions. Then the productive devices are said to be selective. That is the desired feature from the productive devices. So productive devices should restrain from operation. It means they should not operate for transient conditions, and they should operate for fault conditions. That also comes under selectivity. That is the second important feature. Coming to the third, it is sensitivity. So what does sensitivity mean? Sensitivity means when the current in the system just exceeds the pickup value. Okay, current exceeds the pickup value, the relay should operate. So what does this mean? What does this pickup value mean? I have not defined so far what is pickup value. So let me take overcurrent relay for simplicity. We have this overcurrent relay. So it is given, it is fed from CT. Okay. So when CT secondary current goes into the relay, so like this, it is connected. It will be connected to the system like this. Suppose this is load. There is CT here. This is the relay. There will be circuit breaker also. I'm not showing for simplicity. So whatever the CT secondary current goes into the relay. Okay. For this relay, to sense the fault, we should give a setting called pickup setting. Okay. So this, how does this relay distinguish between a fault condition and normal condition based upon the pickup value? Based upon the pickup value. So pickup value is the threshold value of current. Okay. So if the relay coil current, if relay coil current, mind you that relay coil current is nothing but the secondary current of the CT. Okay. So if relay coil current just exceeds the pickup value, then relay should operate. Let us suppose the pickup for this relay is, the pickup value for this relay is 5 amperes. Okay. And if current of 6 amperes will flow into the relay, 6 amperes is flowing, but the pickup given to the relay is 5 amperes, then this relay should treat the 6 amperes current as fault current. Okay. 7 amperes fault current. So whatever magnitude just above the pickup should be treated as fault current. So if the current in the relay is 5.2, just very close to the pickup, still the relay should treat this current as fault current, because that is above the pickup value. Although it is very close to the pickup value, still the relay should consider it as a fault current. If it considers any current above the pickup value as fault current, then the relay is said to be sensitive, and it is a desired feature in protective devices. So protective devices should be sensitive enough to pick up or to operate when the current in the system exceeds the pickup value. Such a feature is called sensitivity. And the last feature is cost. Okay, or economy. Okay, the protective devices that we are installing to protect the power system should be of low cost. After all, these devices are intended to protect the actual power system. We have invested already huge capital investment in the power system, in the generating station, in the transmission lines, and the distribution system. Huge amount of capital is invested, and whole piece of power system is a costly affair. To protect that costly piece of equipment and whole system, we are installing relays and circuit breakers, and we expect this relay and circuit breaker to be of low cost, because the actual task is done by the power system, and these devices are just safety devices. Okay, safety devices. So we expect them to be of as low cost as possible. Okay, so these are the important features of any power system protection scheme or device, any power system protective device: reliability, selectivity, sensitivity, and being economical. Reliability tells us that if the power system protective devices like relays and circuit breaker, if they are able to perform the intended task, they are reliable. Unreliability will occur because of two reasons. One reason is that relays and circuit breakers are not operating when needed. That is one reason for unreliability. Unreliability may also occur because of another reason. That is that these protective devices are operating when not needed. Because of these two reasons, unreliability may occur. Selectivity, they are able to exclusively isolate only the faulty section, and the other part of the power system where there is no fault, that should not be isolated. Okay, selectivity also means that the protective devices should discriminate between faulty situation and transient situation. Sensitivity, protective devices, for example relay, should pick up or should operate when the current in the system just exceeds the pickup value. The fourth and last one is that they should be economical. means the cost involved should be very less compared to the overall power system cost. Very less in the sense somewhere around 5%, 6%. Okay. Thank you. I hope you understood. Please subscribe to Easy BTech channel.